The knapsack problem is a classic optimization problem in computer science. It's often used to help teach dynamic programming and greedy algorithms. This is an important problem to understand, especially if you plan on interviewing soon for a programming job. In this course, Gavin Lon will explain the problem and show how to craft an efficient solution using C#. Gavin has created many popular courses for our channel, and he's also a freeCodeCamp team member. Let's start learning.
Hi everyone, I'm Gavin Lon. Look, I'm in trouble. I've recently been asked to leave my apartment by my landlord. He says the neighbors have been complaining about me causing noise pollution. The bottom line is the police are on their way to forcibly remove me. So I need to grab as much stuff as possible and cram it into this knapsack here. And leave as fast as possible. The problem is I've got a lot of stuff. So which items do I take with me? I need to take the most valuable items so that I can come up with the money for a deposit for a new apartment. But I can only realistically take a few items in this knapsack. I don't even really know what a knapsack is. So I guess this is my knapsack. Okay. It's kind of a rucksack, knapsack, whatever. It's a sack. So the bottom line is I have a knapsack with a finite capacity, which means I can only take a few items with me. So I need a way to fit as much value as possible into my knapsack. This is called the knapsack problem. Luckily, I've been kicked out of a few apartments in my time, so I'm very familiar with the knapsack problem. So, I have a solution to the knapsack problem, which I'm going to share with you before the police come and cart me away. Let's get into this video. In this video, we are going to create an algorithm using C# to solve the famous 0-1 knapsack problem. Let me briefly describe the problem. So we have a number of items, in this case 4 items. Each item has an associated weight and value. So for example, the first item weighs 8 kgs and has a value of $50. The second item weighs 2 kgs and has a value of $150. The third item weighs 6 kgs and has a value of $210. And the fourth item weighs 1 kg and has a value of $30. The problem is, we are trying to decide which items to include within a container that can only hold a certain amount of weight, i.e., the container has a fixed capacity. So in this example, our container will only be able to hold 10 kilograms of weight. So this is called the knapsack problem, but in this video, I'll refer to a container in place of a literal knapsack. We are trying to maximize the total value that can be included within our container. Our code needs to consider each of the relevant items and decide, as it were, if the considered item must be included in the container, which can be represented by a value of 1, or the considered item must not be included within the container, which could be represented by a 0. When we first look at this problem, it looks really difficult. If our code is considering each item and making the decision, as it were, to include or exclude the item, the total number of potential solutions is 2 to the power of n. In this case, 2 to the power of 4, because we are dealing with 4 items. So the time it takes to solve the problem can be expressed in big O notation as big O of 2 to the power of n time. In this video, we'll demonstrate that by using dynamic programming, we can solve this problem in big O of n times w time. N denotes the number of considered items, and w denotes the maximum amount of weight that our container can hold. If you'd like to read more detail on big O notation, I've included an appropriate link below in the description. So we are going to go through the code to solve the 0-1 knapsack problem step by step to ensure that we understand how the relevant algorithm works. So basically the problem is, we need to choose the items where the sum of their values gives us the greatest amount of value when compared to the other possible combinations of items that can be included within our container. So this is an optimization problem that we need to solve. For the purposes of this video, we are going to keep this problem really simple. We have a container that can fit items that weigh less than or equal to 10 kgs. If the sum of the weight proposed, as it were, for a potential solution is greater than 10 kgs, this combination of items will not work. We cannot take all of those items because their combined weight exceeds the 10 kg limit. So we need to include the items where their combined weights do not exceed 10 kgs and the sum of the value of the items that we wish to include in the container is greater when compared to the other possible combinations of items that can be carried within our container. The problem is drastically simplified in this example. If, however, we were to scale up the problem where, for example, we have a large shipping container and potentially hundreds of items, this would take most human beings too long to calculate in a time frame that could be deemed as efficient. So this is where our algorithm becomes essential. In, for example, shipping, this type of algorithm that we are about to implement would run on a daily basis. We are going to use the bottom-up approach to dynamic programming to implement the relevant algorithm to solve our problem. This is in contrast to the top-down approach. We could write our algorithm using the top-down approach, but we can avoid writing recursive code by using the bottom-up approach. The approach to writing our algorithm will involve a strategy called memoization. Very basically, memoization ensures that a function doesn't run for the same inputs more than once by keeping a record of the results for the given inputs. Let's briefly look at a depiction of how the algorithm processes each item in relation to the capacity of the container. The algorithm appropriately considers each item's relevant data, i.e., weight and value. Each row denotes a considered item. Each column denotes the container's capacity, which grows, as it were, by a value of 1, until the final value is reached, which is the capacity of our container, in this case 10. The algorithm traverses each row from left to right. For each cell in the table or each position in the two-dimensional array, the algorithm appropriately evaluates the weight and value of each considered item in relation to the currently considered capacity of the container. The algorithm then appropriately computes the maximum value that can be included in the container depending on the considered data. The computed value is then recorded at the appropriate position in the two-dimensional array. The relevant two-dimensional array used for memoization is depicted by our table here. This is so that we can visualize how the algorithm progresses and calculates the relevant values. Our algorithm will repeat the relevant computational pattern until it arrives at the final result, which will be recorded in the bottom right cell of the table here, or position 4, 10 of the two-dimensional array used for memoization. The final result is the maximized value of the items included in the container. Right, let's write the code for our algorithm. Let's create a .NET Core console application within Visual Studio. So let's write the pertinent details of the relevant items and the container involved in this particular scenario in a comment at the top of the main method. We are going to store the detail of each item's weight and value appropriately within two separate arrays. So let's first create a one-dimensional array named weights and add the relevant weights of our items appropriately to the weights array. Let's create another one-dimensional array named values and appropriately add the values associated with each of our items to the values array. I briefly mentioned the technique of memoization earlier. So let's create a two-dimensional array named data. This array will enable us to keep a record of essential values that are computed as the execution of the algorithm progresses. Let's define an integer constant named n that stores the number of relevant items. Let's define the capacity of our container. So in this example, our container can hold a maximum weight of 10 kgs. Let's create two for loops, an outer for loop and a nested or inner for loop. The outer for loop loops through n number of items, which in this example is a value of 4. Each increment of the inner for loop denotes the weight that can be held within the container at a particular point in the execution of our algorithm. So for example, at increment 3 of the inner for loop, the algorithm will consider whether an item can be included within the container if the container can only hold a weight of 3 kgs. When the increment is 4 for the inner loop, the algorithm will consider whether an item can be included within the container if the container can hold a weight of 4 kgs, and so on, until the incremented value of the inner loop hits the max capacity, which is a value of 10, at which point the inner loop is exited. So here we have a table that depicts the two-dimensional array we have named data. As discussed, the data array is used to store the results of computed values, which are appropriately recorded as the algorithm progresses towards a conclusion. This represents the two-dimensional array that we have named data in our code. So, within the inner for loop, we need to implement code that will appropriately compute the values of the items that can be included in the container at appropriate points in the execution of our algorithm. The computed values are then inserted at appropriate positions within the two-dimensional data array. So firstly, we need to write code that evaluates the value of the item num variable that represents an item in our example. So if the item num variable's value is 0, code to insert the value of 0 into the appropriate position in the data array must be executed. So if you look at our table, you can see that these cells in the top row will all contain the value of 0. Considering 0 item or 0 capacity for the container may seem redundant, but having these values within the data array is essential to the working of our algorithm. This will become clear as the video progresses. If the item num variable's value at this point is not 0, our code must evaluate the value stored in the capacity variable. So let's write the code that must execute if either the item num variable is 0 or the capacity variable is 0. All we are doing here in this line of code is recording a value of 0 at appropriate positions in our two-dimensional array. Then if neither the item num variable is 0 or the capacity variable is 0, we need to write code that makes another evaluation. So we can implement the relevant evaluation code using an else-if statement like this. So here we are saying with this else-if condition, if the weight of the considered item is less than or equal to the considered capacity, i.e. the maximum allowable weight for items to be held within the container at this point in the execution of the code, we need to make a specific computation before storing the relevant computed value at the appropriate position in the data array. So if the else-if condition returns true, we need to use a formula to compute a value before storing the value at the appropriate position within the data array. So let's take a quick look at the formula. We can use C#'s math.max static method to implement the relevant formula. So the first argument that we need to pass into the max method can be computed like this. The second argument is as follows. The max method simply returns the greater value of the two arguments passed to it. Then we can write code to record the value returned from the formula in the appropriate position in our two-dimensional data array, like this. So if the conditions in the if and the else if statement both return false, we need code to execute that inserts the value stored in the cell directly above the considered cell, as it were, at the appropriate position in the data array. So to do this, we must write this line of code within the else block. And that's it. That is the code implementation for our algorithm. Then we can write code to output the final result to the screen. The final result is found at position n, max capacity, so position 4, 10 in our data array. Let's run the code. And you can see that we are presented with the correct answer. The result is the value of 390. We can include the drone, the monitor, and the kettle within our container, which gives us the value of $390. So let's go through the execution of our algorithm in more detail so we can get a clear understanding of what is going on during the execution of the algorithm. So for the first row in our table, all of the cells will be set to 0 because at the points of execution of our algorithm pertinent to these cells in the top row, the item num variable is equal to 0. So the code in the if block will execute. So we can fill in 0 for the top row in our table. Remember, this depiction represents the two-dimensional data array that we are using for memoization in our algorithm. So now let's consider the data associated with the first cell in the second row, which maps to position 1, 0 in our data array. Our algorithm at this point is considering relevant data for the first item, which in our example is the microwave. The considered capacity is equal to 0. So the value for the first cell in the second row will be 0. Then for the second cell on the second row, the considered capacity is 1, and the item's weight, the microwave's weight, is 8. So the if condition returns false, and the else if condition also returns false. If we look at the condition in the else if statement, the weight of the microwave is greater than the considered capacity of the container in the else if condition. And so the else if condition returns false. So this means that the code in the else block will execute. So in this case, we can insert the value stored in the cell directly above the cell that is currently being considered, as it were, into this cell, the cell that we have just considered. This depiction, of course, analogously represents the appropriate value being recorded at an appropriate position in the two-dimensional data array. You can see that the code within the else block implements this functionality. If you think about it in practical terms, at this point in the execution of the algorithm, the code is considering if the microwave, which has a weight of 8 kgs, can be stored in the container when it has a capacity to hold 1 kg of weight. This is of course not possible, so by recording 0 at this point, we know that no item can be stored in the container at this point. So this same logic applies until we reach a capacity of 8. So let's record 0 up until the capacity is equal to 8. So when the container can hold 8 kgs of weight, capacity is equal to 8, this means at this point we can include the microwave in the container, because as discussed, the microwave has a weight of 8 kgs. The relevant condition can read as if the weight of the currently considered item is less than or equal to the currently considered capacity. Run the formula, i.e. the code within the else-if block. So the else-if condition returns true because the weight of the considered item is equal to the currently considered capacity, which is a capacity that can hold 8 kgs. So let's look at the formula that runs to calculate the value that will be recorded at the appropriate position in the data array. So the algorithm at this point evaluates using C#'s max method which of two values passed as arguments to the max method is greater. The greater value of the two is returned from the max method. So let's get the values that will be plugged into the formula, i.e. the values for the two relevant arguments that will be appropriately passed to the max method. Let's look at the first argument. So here we are considering the microwave. The microwave has a value of 50. So we can plug 50 into the formula here. Then in order to get the value for the first argument passed into the max method, we must add the value stored at this position in the data array to the value of the microwave, i.e. the currently considered item. So let's get the value stored in the data array at position 0, which is the currently considered item number 1 minus 1, comma, the current considered capacity 8 minus the weight of the currently considered item, which is also 8. So we add the value stored at position 0, 0 in the data array to the value of the microwave, which is a value of 50. So we pass 50 as our first argument into the max method. The second argument can be found at position 0, 8 in the data array, which as you can see in our table is 0. So obviously the greatest value between 50 and 0 is 50. So the max method returns 50, and our code runs that stores the value of 50 at the appropriate position in the data array. So when the considered capacity is 9, the considered capacity is greater than the weight of the considered item, the microwave, which is 8 kgs. So the code that we have just examined also applies for when item num equals 1 and capacity equals 9. So we can record 50 at the appropriate point in the table, representing that this value has just been recorded at its counterpart position in the data array. The same code is also run when the code considers the microwave, which weighs 8 kgs, against the capacity, which can hold 10 kgs. So let's record 50 at the appropriate position in our table. Next, the code execution moves on to consider the second item, the drone in this case. So the incremented value in the outer loop, item num, will be 2. The inner loop will evaluate each capacity consideration from 0 to 10 for item 2, incrementing the capacity by 1 with each iteration of the inner loop. So at 0 capacity, of course, we need to include a value of 0 here. When the considered capacity for our container can hold 1 kilogram, the drone has a greater weight than 1 kilogram. The drone weighs 2 kilograms, so the code in the else block is executed. So let's record this value at the appropriate position in our table. Then the code considers a capacity for our container where it can hold 2 kgs. Our drone weighs 2 kgs, which means the drone can be included in the container. So the code within the else-if block is executed. So let's plug in the relevant values into our formula. So the first argument passed to the math.max method is the value of the drone, which is 150, plus a value of 0. The second argument is 0, so of course 150 is greater than 0. So let's record the value of 150 at the appropriate position in our table. The same values are processed by the formula in the else-if block until the capacity reaches a value of 8, i.e. where the code evaluates the container's capacity where it can hold 8 kgs. Each considered capacity from 2 to 7 for when the drone is considered has resulted in our formula processing the same values. However, the values that will be plugged into our formula will be different when the capacity is 8. So let's appropriately fill in the values up till when the capacity is 8. So when the capacity is 8, the first argument passed into the max method is the value of the drone, 150, plus 0 found at this position in the data array. The second argument passed into the max method is the value of the microwave, 50. So obviously 150 is greater than 50. So here we record the value of the drone, 150. When we consider the scenario presented to us with the next iteration of the inner loop, i.e. when the capacity is 9, we need to record 150 once again. This is the value returned from our formula implemented in the else-if block. However, when we consider the scenario presented to us with the final iteration of the inner loop for the currently considered item, i.e. when the capacity is equal to 10, at this point we can include both the microwave, which weighs 8 kgs, and the drone, which weighs 2 kgs within our container, because at this point our code is considering a capacity of 10, and our code is considering the second item, the drone. So here you can see that the first argument is the result of a calculation of the value of the microwave plus the value of the drone, which equals 200. The value of the second argument is the value of the microwave, 50. So 200 is obviously greater than 50, so 200 is returned from the max method, which means 200 is recorded at the appropriate position within the data array. At this point, our code has recorded all relevant values in the data array regarding the microwave and the drone. These items have now been considered against all relevant capacity considerations. So the next increment for the outer loop executes, and the next item, the monitor, will be considered against each relevant capacity. So our code now considers the third item. The item num variable defined in the outer loop is now equal to 3. 3 represents the monitor. The monitor weighs 6 kgs and has a value of 210. So at position 0 in the fourth row, 0 must be recorded because the value stored in the capacity variable is 0, so the code in the if block is executed. So when the capacity variable is equal to 1, code in the else block is executed because neither the capacity or item num variable is equal to 0, and the weight of the monitor, which is 6 kgs, is greater than the currently considered capacity, 1. So this means the value in the cell directly above the position that is being considered, as it were, must be appropriately inserted into our table at the appropriate position, the cell that we have just considered. So now the capacity is equal to 2. We can see here that the value directly above the considered position, as it were, is 150, which is the value of the drone. The code within the else block is executed and a value of 150 is filled in at the considered position. So the code within the else block will repeat until the capacity variable is equal to 6, which means if the container was empty and had the capacity to store a maximum of 6 kgs, that the monitor could be included in the container. Let's appropriately fill in the values in our table until the capacity equals to 6. At this point, the weight of the considered item is the same as the value of the capacity variable, so the code in the else-if block is executed. So let's plug in the relevant values into the formula. So the first argument passed into the max method will be the value of the monitor, 210, plus 0, which gives us a value of 210. The second argument passed into the max method will be a value of 150, the value of the drone. 210 is obviously greater than 150, so 210 will be stored at the appropriate position in the data array here. The same value is appropriately recorded for the scenario that is presented to us in the subsequent iteration of the inner loop, i.e. when the capacity variable equals to 7. So we can record 210 here. So when the capacity is equal to 8, the values that are plugged into our formula are different to the values passed into the formula when the capacity was 6 or 7. So let's plug in the appropriate values into the max method. The first argument has a value of 210 plus 150, which equals to 360. The second argument is 150, so 360 is greater than 150. So let's fill in 360 here. So when the capacity variable equals to 9, so the value of 360 is appropriately recorded. Let's plug in the appropriate values into our formula when the capacity variable reaches 10. The first argument will be 210, the value of the monitor, plus 150, which is the value of the drone. This gives us a value of 360. The second argument comes from the cell directly above the current cell, which is the value of the microwave, 50, plus the value of the drone, 150, which gives us a value of 200. So 360 is obviously greater than 200, so we can record 360 as the value in the current cell. So we can now consider item 4, which is the kettle. The kettle has a value of 30 and weighs 1 kg. So in the first cell of this row, we can record a value of 0. Then in the second cell, where the capacity value is 1, we can plug relevant values into our formula to compute the value that needs to be recorded in the current cell. The kettle weighs 1 kg, and the code is considering a capacity of 1. So the weight of the item equals to the considered capacity. So code within the else if block is executed. So the first argument passed into the max method is the value of the considered item. So the value of the kettle is 30 plus 0, which gives us a value of 30. The second argument passed into the max method is the value recorded above the current cell, which is a value of 0. So we can record 30 in the current cell. So when the capacity variable is equal to 2, we can pass in the value of the kettle plus 0 as the first argument into the max method. So here we pass in a value of 30. The second argument we need to pass into the max method comes from the value that resides in this cell directly above the current cell, which is the value of the drone, 150. So now, when the capacity that we are considering is 3, the first argument's value will be 30 plus 150, which gives us 180. So that is the value of the kettle plus the value of the drone. The second argument will be the value of the drone, 150. So of course 180 is greater than 150. So let's record 180 here. The next values we need to record are derived from the same computation as the one made when the capacity equals to 3, until the capacity value reaches 6. So let's fill in the value of 180 appropriately until the capacity is 6. So let's plug the values into our formula for when the capacity variable is equal to 6. So the first argument that we need to pass into the max method is the value of the kettle plus the value of the drone, which gives us a value of 180. So we can pass 180 as the first argument to the max method. As always, the second argument that we need to pass into our max method comes from the cell directly above the current cell. This cell contains the value of the monitor, so 210 is obviously greater than 180, so we can record 210 in the current cell. When a capacity of 7 is considered, the first argument passed to the max method is the value of the kettle plus the value of the monitor, which gives us a value of 240. 240 is greater than 210, so we can record 240 here. When a capacity of 8 is considered, the first argument passed into the max method is the value of the kettle plus the value of the monitor, which gives us a value of 240. when compared to the value directly above the considered position, as it were, which is 360, 360 is obviously greater than 240, so 360 is returned from the max method and appropriately recorded within the data array. When the capacity of 9 is considered, the first argument passed into the max method is the value of the kettle plus the value of the monitor plus the value of the drone, which gives us a value of 390. When comparing the value of the drone plus the value of the monitor, which gives us a value of 360, to the value of 390, of course, 390 is greater than 360, so we can record the value of 390 here. The final considered position, as it were, involves the same calculation as when the capacity was equal to 9, so we can record the value of 390 here. This is our final result. We have maximized the value of our container with a value of 390. And you can see how this algorithm works when we look at the results in the table. The maximum value is being calculated for every scenario until the final capacity and number of items has been considered. So if our container could only accommodate a maximum weight of 6 kgs, and we were only considering the following items, the microwave, the drone, and the monitor, we must only include the monitor in our container to maximize our value. We can see what the value will be if we look at our results in our table here at this position. If we were considering those same 3 items and our container could only hold a maximum of 8 kgs, we would include the monitor and the drone within our container, which would give us a value of $360. We can see this in our results here at position 3,8 in our data array. If we were only considering the drone and the microwave, and our container could hold a maximum of 8 kgs, we would only include the drone in our container to maximize our value. So as you can see in our results, when we are considering all 4 items and our container can hold a maximum weight of 10 kgs, we must include the drone, the monitor, and the kettle to maximize the value in our container. This gives us the value of $390. Using the bottom-up approach to dynamic programming, we were able to calculate this value in big O of n times w time complexity. N represents the number of items considered, and W represents the capacity of our container. The capacity is the amount of weight that the container is able to hold. So let's now write the code that will use the data accumulated by the algorithm we have just written to tell us which items need to be included in our container to achieve the maximum value calculated by the algorithm that we have just written. Before we write the code for this, let's neaten up the existing code a bit. So we can put the code for the algorithm in its own function, like this. The values that define the problem can be passed into this function from the calling code, which will be code implemented in the main method. The function, of course, returns the result computed by our algorithm that we have implemented to solve the 0-1 knapsack problem. Let's run the code. Great. So let's create a new function that will output the inclusion or exclusion status for each of the items considered in our application. You can see here we have a parameter which is a string array named item names. So we need to pass in an array containing the names of the items that are relevant to our problem into this parameter. So let's go to the main method, define a one-dimensional string array, and appropriately add the names of the relevant items to the array. The appropriate details of the items that are excluded from the container will be outputted with a red background color. The appropriate details for the items that are included in the container will be outputted with a green background color. So in the method that runs the algorithm that accumulates the relevant data in the data array, the algorithm started from position 0, 0 in the data array and worked from left to right for each row in the two-dimensional array named data, computing relevant values and recording those values at the appropriate positions in the data array. When the algorithm completed, the final result could be found at position n, that defines the number of items relevant to the problem, comma, max capacity. That defines the maximum weight that the container can hold, the container's capacity. So the final result can be found at position 4, 10 of our data array. In contrast to the way the algorithm worked, the code that we are going to write here will work backwards from the position of the final result, i.e. position 4, 10, until all relevant data has been considered and all relevant data has been outputted. So firstly, let's initialize two variables. Let's set a variable named I to the value that will be passed as an argument to the parameter named n. N denotes the number of items relevant to a particular problem. Let's set a variable named j to the value that will be passed as an argument to the parameter named max capacity. The max capacity parameter denotes the maximum weight that the container can hold. Let's create a while loop that terminates when either I or j is equal to 0. So the while loop will continue to execute while I is greater than 0 and j is greater than 0. The loop will terminate when either I or j is equal to 0. So within the while loop, let's include an if condition that evaluates whether the value at position I, j, the considered item, is equal to the value at position I minus 1, j. If the compared values in this condition are equal, code must execute to output the details of the considered item with a background color that is red, indicating that the item is excluded from the container. We'll write the code to change the background color of the text accordingly in a bit. Conversely, when the if condition is false, code must run that outputs text denoting that the considered item is included in the container. This will be indicated by giving the relevant text a green background. So at the position immediately after the if-else code to decrement the I variable by a value of 1 must be implemented. So we are looping backwards through the items in the data array. After code is run, in the case when an item is deemed to be included in the container, i.e. within the else block here, we must update the value of j by subtracting the weight of the considered item from the current value of j. So the code within the while loop will repeat until either j is equal to 0 or I is equal to 0. So that is the logic for the code that outputs text denoting items included in the container and the items excluded from the container. Let's write a reusable function that outputs text with appropriate background colors. A red background denotes an item that is excluded from the container. A green background denotes an item included within the container. So let's first write an enum that contains 3 list items. Let's name these items normal, success, and danger, respectively. Let's write a method named writeTextToScreen. This method contains 2 parameters. So the logic for this method simply changes the color for the outputted text based on the argument passed into the second parameter. So for our purposes here, if the item is included in the container, the text is white and the background color is green. If the item is excluded from the container, the text is white and the background color is red. So we can now use our write text to screen method appropriately in our code. Let's run the code. Excellent.